start out with. So the first topic we're going to explore in this potpourri of mathematics that we're going to be pursuing to end the third quarter is on radical and rational exponent expressions. Things, in other words, with types of roots in them. That's what a radical means. Radical is another name. It's the more precise name for like square root. A square root is a type of radical. There's, of course, other types of radicals as well, like cube roots, fourth power roots. There's any power of roots. Those are also called radicals. Okay? And we're also intimately related to radicals are rational exponents. Rational, of course, means fraction. We've used that word lots of times now, I think. So we're going to see fractional exponents. Those they basically are the same thing as roots. So we're going to study them at the same time. So let's have a look. So I thought if we started with just a pretty basic general root or radical expression, we could break it down into cases and think about some examples of what could happen before we start looking at these in more depth. Okay? So I broke it into 3 cases. I wonder we might need one more case. So what if the thing that you're rooting, regardless of what power of root it is, what if it's 0 inside that square root? Like, what's the square root of 0? If you're not sure, try your calculator. Remember, when you say square root, you're asking yourself what times itself is equal to that thing. So what times itself is equal to 0? I think the only thing that does that is 0, right? The only thing that times itself that's equal to 0 is 0. There's lots of other things multiplied by 0 where you get 0, anything in fact. But something times itself, the only thing that's going to work is 0. So the actual answers, the roots are 0. Examples of that might be like the square root of 0. If we don't put a 2 there, it means square root, right? But you can put a 2 there if you want to clarify. We just usually don't. The 5th root of 0 would be 0. The 113th root of 0 would be 0. Okay, so that's kind of the most simple thing. So when we go to graph these, starting on Thursday, they're all going to go through the origin. All these types of root functions must go through the origin. If when you put in 0, you get out 0, right? So let's remember that when we look at the graphs. Okay, what if we've got an odd root, not a square root then, something like the cube root of the 5th root, or something like that? Let's think of some examples. Things like the cube root of 27. How about the 5th root of negative 32? Or the cube root of negative 27? Let's just do those and see if we can figure out what's happening here. So what do you guys think? What is the cube root of 27? Go back to your power tables. What times itself 3 times is 27? The answer is, of course, 3, right? How about the cube root of negative 27? Do you get an answer for that?
Yeah.
Good guesses. I like that. That's a good idea. But remember, you're asking yourself, what times itself 3 times will be negative 27? I think there's a real number that works. In fact, let's do an easier one first. Let's do the cube root of negative 8. Is that going to be something with I? I think the answer is negative 2. Let's check it, because if you go negative 2 times negative 2 times negative 2, what do you get? That's 4. And there's your negative 8 that you guys are telling me. So if you cube root a negative number, does it exist or not in the real numbers? Looks like it does. So I'm thinking the graph will also go into negative land for cube roots. And I think 5th root's the same thing. What's the 5th root of negative 32? Can somebody help me with that one? What times itself 5 times gives you negative 32? I picked something nice, right? 32 is 2 to the 5th power. So this is the same thing as saying what's the 5th root of negative 2 to the 5th power? Well, it's negative 2 because the 5's cancel. Okay, so it's looking like if n is odd, the roots, let's just write ourselves a note. The root is going to be a positive root if the thing inside, I called it y, is positive, right? And I think so far for our examples, at least, it's going to be a negative answer, a negative root. If what? If the inside is negative. Okay, so how about square roots and 4th power roots and things like that? So Of course, we have good friendly ones like we're used to, like a square root of 144. We could have the fourth root of 16. We could do the fourth root of negative 16. What's the square root of 144? Is it just 12? Remember, 12 times 12 is 144, but also negative 12 times negative 12 is 144. That's why you get that plus or minus side effect when you do something like that, right? When you operate with the square root. So how about the fourth root of 16 then? What times itself 4 times gives you 16?
2.
It's 2, but it could be negative 2 as well. So if the thing inside is positive, so if we have, I don't know, you can write this however you want, we get 2 plus and minus roots if y is positive. That's one thing. How about the fourth root of negative 16? You're saying you're arguing for I, Jacob?
Yeah.
You guys agree this time or not? If we do negative 2 times negative 2, you get 4. Times negative 2, you get negative 8. Times negative 2, you get positive 16, not negative 16. And if I do it with positive 2, it's definitely not going to give us negative 16, right? So is there some other answer that's going to give you that? And I think the answer is no. This guy's undefined. Or let's say maybe something I. And I think yes, plus or minus 2i would work here, but for the purposes of this, let's just remember that there's no real answer, okay? That's all we're going to have to worry about. So, put no roots. There are no real roots, let's specify it like that. No real roots. You have to go to complex numbers. So no real roots if the inside is negative on that one. Okay? So those are all the possible things that can happen when you're working with a radical expression. We just covered everything. Everything that could possibly happen. Of course, all my examples here came out as nice numbers. They're not always going to be nice. I mean, you might have to use your calculator once in a while, but most of the problems in your practice set are going to come out pretty nice as well, I think. Okay? So let's look at some examples. Okay, so we got 4 problems up here. The A problem says something like simplify, make these root or radical expressions a little bit easier to think about. So I think there's 2 properties that we're going to need to do that. But let me just start doing the problems first, and then you guys can tell me maybe what the properties are in a sec. They should be things you saw in Algebra 1 as well, but we'll see. So this one says take the cube root of 27x to the 6th power. I think you'll find when you're doing these, the variable parts are the easiest. Let's see if you guys agree with me. So since this is a cube root, what you want to do is take the stuff inside and try to put it into cubes. You want to arrange it into cubes so that you can get stuff that cancels, okay? So cube root of 27x to the 6th. Well, the number part is the part that might give you a little trouble sometimes. This one's pretty nice because the cube root of 27, didn't we just do that? That's from our power tables. Cube root of 27 is a cube number. It's 3, right? But if you really wanted to, you could write it as a power of 3. So we know that 27 is 3 cubed. That's kind of unnecessary on this problem, but you'll see it might be necessary on some others. Okay. So 27 is 3 cubed. How can I write this in terms of powers of 3? Well, let's just write x cubed, and then how many more x's do I need if I want them to add up to 6? Well, I need 3 more. You can write this in whatever combination you want, right? Like there's x times x times x 6 times. So I wrote it in 2 packets of 3. Why'd I do that?
Because it's cubed.
It's cubed, and cube root cancels. Cube root cancels power of 3. So now these all cancel. You guys see how everything cancels on this problem? And there's not going to be any cube root left at all. Cube root of 3 cubed is 3. Cube root of x cubed is x. Cube root of x cubed is x. So the answer is 3x squared. Okay, so you don't have to write this out every time, but I'm going to do it on a couple just to make it clear to you, and then it's your choice how much you write it out. Brittany?
Could you show that just one more time so you got like 3x cubed?
Yeah, I'm going to do it on this one too.
Okay.
Let's see if it makes sense after this one. So 4th root of 81, x to the 12th. Some of you guys are probably already almost to the point where you can just do that in your head now.
Yeah.
The rest of us are probably going to take a little bit more time. So what powers should I be trying to rewrite the stuff on the inside in terms of? What power? 4th power, because it's a 4th root, right? So I want to try to break this down into 4th powers. The variable is going to be easy. 81 might be a little tougher. So break it down however you want. If you really know your power tables, you know that 81 is what? Anybody know? 3 to the 4th power. So that's the fast way. But some of you guys aren't going to recognize that. So say 81. Just divide it however you want. Divides by 9, doesn't it? 9 times 9. And then each of the 9s is 3 times 3. So you can see there's the prime factorization. There's the number at its very most basic elements, most basic components, its most basic prime factors. And so I can see that really inside that 4th root, let me get it in black here. Inside that 4th root I have how many 3's? Well, 3 times itself 4 times. Makes sense? So that's already as a power of 4. Look at that. Worked out really nice. It's not going to work out that nice every time, but so far it did. And then x we're also going to write as powers of 4. So I'm going to say, all right, 4, and just keep doing it till you run out. 4, that's 8 now. How many x's do I have left to get to 12? 4 more. So this is really coming out pretty nice still. So everything's going to cancel. So I'm going to get 3, and x will, 4th power cancels x to the 4th 3 times, so we're going to have 3 x's that come outside, and there's no radical left at all whatsoever. Okay? So the thing is, a lot of problems you're going to have leftovers. There's going to be stuff left inside the square root or left inside the 5th root, and that's okay. So let's see if that happens on number 3. So number 3, we're breaking stuff on the inside into powers of what on this one? Use the index on the radical, so powers of 3. So we're going to say, okay, powers of 3. Let's see what happens. Well, at the top we're going to have 9, 12, 15, and then just an x to the 1 right there, right? And on the bottom, 8. Break it down. You could say it's 4 times 2, and the 4 is 2 times 2. So break it down however you want, or just recognize it for what it is. It's up to you. Okay. And that's already at power of 3, so I don't need to touch it at all. Let's see, do we have any leftovers this time? I think everything's going to cancel at the powers of 3 except for that guy right there. So how many x's are going to pop out on top?
5. Oh.
5 times, yeah. Yeah, you're right.
Okay.
X times x times x, 5 times on top. There's going to be some leftovers on top, aren't there? Yeah. This guy's stuck. He can't come out. He's going to be stuck inside there. And then on the bottom, everything comes out as well, right? Cube root cancels cubed. So there's a 2 that comes out. Cube root cancels cubed. So there's a y that comes out. So that's the answer. So some of your problems are definitely going to have a root or radical left in them. You just want to take as much outside of the radical as you can. And later on in future classes, you'll see sometimes you need to take stuff out of radicals, sometimes you need to shove stuff back inside of radicals. I mean, it kind of depends what your purpose is. We're just starting to work with that a little bit. Okay? That's where we're at. Yeah. Yeah, it's divided by everything. So I'm using properties of square roots here. Let's do a couple more, and then we'll try to write those properties down. Let's leave this one till tomorrow. Let me do just one more. So let's do that guy tomorrow, and let's go 5th power, and let's go 320 m to the 10th, x to the 13th, z to the 27th. So I just totally made that up off the top of my head, right? So we should be able to simplify it. I made it definitely intending to have some leftovers. So we want to break stuff inside down into powers of 5. Good. So we're going to say, all right, powers of 5 is our goal. So let's do all the variables first. That 320 is probably the part that's a little iffier. So I'm not going to do this by writing it out as many times, because that gets annoying. So I want the closest power of 5 to 13. What's the closest one as an underestimate? 10, right? 5 goes into 10. So I'm going to write this on the bottom as 10, and I'll have 3 leftovers. You guys see that? And then the closest power of 5 to 27, if I round down, is 25. So we'll have z to the 25th, and how many leftovers there to get to 27? 2, right? Remember, you can write things like this in any way you want. I'm trying to match that power of 5 so I can cancel stuff and take it outside. Okay, same thing on top. I'm going to leave the 320 alone. Oh, that's already a power of 10, so you know what, I'm just going to leave that alone. So the 320, how are we going to do that? Well, you could use your calculator to assist you. So 320, you can start breaking it down. Without our calculator, what definitely goes in? 2, yes, bigger numbers though. 10. 10 times 32. And 10 you could keep breaking down more. 32 you could keep breaking down more. But what power should we really be searching for in these numbers? Powers of 5. So when I made this in my head, 32 is a number I picked. Because 32 is what? You can break it down or take a whole bunch more steps to cover this side of the board. The 32 is 2 to the 5th power. That's its prime factorization. 10 you can say is 2 times 5 if you like. But notice, I've got 5 2's. Really, I have how many 2's? 1 and 5. This is all multiplied. Really, I have 6. So it's kind of up to me. I can write this as 2 to the 6th times that 5. Or I can do what I did with all the variables and write this as 2 to the 5th. And how many leftover 2's do I have? 1, and then I also have a leftover 5. It's kind of up to you. As soon as you spot that 5th power, now you're ready to cancel. The hard work's all done. We're ready to cancel and see what happens. So let's see here. 5th power cancels that, so 2 comes out. How many m's come out? It's going to cancel. It's like m to the 5th, m to the 5th, so you're going to have m squared come out. And then 5th root, we're going to have these guys as leftovers. So I'm going to rewrite it as 10. And on the bottom, I have how many x's come out because of this x to the 10th? 2 of them, so you get x squared. Those are going to stay stuck. How many z's are going to come out here? 5 of them. And then we've got some leftovers in here as well. So those are stuck, and those are stuck. You're going to have to stay inside the 5th root. And that's it. So that's a form of the right answer. These could be condensed. It's kind of a judgment call. You could bring this all together and make it look a little prettier. And say this is really just a 5th root right here of 10 over x cubed c squared. That's kind of your choice. That's how you simplify with radicals. The goal, again, is to take as much out of the radical as you can. Sometimes there'll be leftovers, sometimes there won't. So the 2 properties, what are the 2 properties that we're using behind the scenes for these problems? I'm going to write them on the board, and as you're working your problems, think about where you're using them. So I think we're using the property that for any root, so I'm going to say n, doesn't matter, of a times b, you can split it up like that, if it's multiplied. And I think like on this last problem, I used this property a couple times. If you have division inside of any kind of root, then you can split it up and put one over the other. So I think I use these properties on just about, well, not just about every step, but many, many steps that I was using there. They're pretty intuitive. So you can split apart radicals if they're multiplied or divided. Do you think you can split them apart if there's a plus or minus? No. The answer is no. We'll see some situations where you're tempted to do that. Okay?